discuss another problem in electromagnetic waves. That is, a long coaxial cable carries a current I, where the current flows down the surface of inner cylinder radius A and back along the outer cylinder with radius B as given in the figure. This is the inner cylinder with radius A and this is the outer cylinder with radius B. And the first question is, find the energy stored in a section of length L. And the next one is, calculate the power transported down the cables. We can go through the solution. The solution for the A part, for that consider the general equation for the energy stored in an electric field, that is W is equal to 1 by 2 mu 0 volume integral B square d tau. And from the electrodynamics 1 we have already derived the expression for magnetic field between the two cylinders, that is mu 0 I by 2 pi r unit vector phi. So we can substitute for the magnetic field here, that is W is equal to 1 by 2 mu 0 volume integral mu 0 I by 2 pi r square d tau, and we know for the cylindrical coordinates d tau will be r dr d phi dz. That is d tau will be r dr d phi dz. That's equal to, we can take the mu 0 I divided by 2 pi whole square to outside, 1 by 2 mu 0 I by 2 pi square, and we can split the volume integral according to these elements dr, d phi and dz. That is r is equal to a to r is equal to b, 1 by r square into r dr. Integral phi is equal to 0 to 2 pi d phi, and integral 0 to z equal to 0 to L dz. That is, we are considering the energy stored in a magnetic field of section L only, with a length L only. So this will be equal to mu 0 square I square by mu 0 got cancelled, then mu 0 I square by 8 pi square, and here integral a to b dr by r into, by integrating 2 pi into L. That is, here it will be equal to mu 0 I square into 2 pi into L divided by 8 pi square into log r to the limit a to b. That is equal to, we can rearrange this equation, pi and pi got cancelled, mu 0 I square to 8, that is remaining 4 only, mu 0 I square L divided by 4 pi log b by a. This is the solution for the energy stored in a magnetic field with a length of the section as L. Next sub question is, we have to find out the power transported down the cables. To get that, we have to calculate the Poynting vector. For that, we have to know the expression for electric field and magnetic field. From the previous electrodynamics 1 paper, we have already derived the electric field in the space between cylinders, that is lambda by 2 pi epsilon 0 r unit vector. And the magnetic field in the space between cylinders, that is mu 0 I by 2 pi r unit vector phi. So, the energy transported per unit area per unit time, which is normal to the directional propagation of electromagnetic wave, will be the Poynting vector S is equal to 1 by mu 0 E cross B. That is, S is equal to, Poynting vector S is equal to 1 by mu 0 E cross B, means E is equal to lambda by 2 pi epsilon 0 r unit vector r cross B mu 0 I by 2 pi r unit vector phi. So we can take outside these magnitude terms, that's equal to 1 by mu 0 and mu 0 got cancelled, and the remaining lambda I by 2 pi into 2 pi, that is 4 pi square epsilon 0 r unit vector r cross phi. As we know, we are dealing with the cylindrical coordinate system r phi z. Then in this case, r cross phi will be equal to unit vector z, that is lambda I by 4 pi square epsilon 0 r square. Here is r square. R square unit vector z. Aim is to find out the energy per unit time or the power transported out of the surface. So, we have discussed or derived the expression for Poynting vector, which is representing the energy transported per unit time per unit area. So, in order to find out the energy flowing per unit time, we have to integrate over surface S dot dA. We know S is equal to surface integral lambda I by 4 pi square epsilon 0 r square, and dA element will be r dr d phi. And I am going to split with respect to dr and d phi, that is equal to lambda I by 4 pi square epsilon 0 line integral, that is the limit r is equal to a to b, r by r square, that is dr by r, surface integral 0 to 2 pi, phi is equal to 0 to 2 pi d phi, which is equal to lambda I by 4 pi square epsilon 0 to 2 pi d phi will be equal to into 2 pi and integral a to b dr by r, that is log r to the limit a to b. And we can cancel the 4 pi square with the 2 pi, and the remaining is lambda I by 2 pi epsilon 0, and applying the limit, this turns to log b by a. This is the expression for the power transported or the energy per unit time in the considered cylindrical shell with the inner radius a and outer radius b. Thank you.